For Design Project 2, we were supposed to build an audio preamp that involves 3 parts. Part 1 is the volume control, Part 2 is the tonal control, and Part 3 is an optoelectric communication link. The volume control, as the name suggests, is mainly focused with controlling the volume output from the circuit. The tonal control has 2 different knobs, one which controls the decibel gain for bass frequencies and one which controls the decibel gain for treble frequencies. The optoelectrical link runs a source through a laser, a LED, which goes to a photoresistor to control the output.
Go.
The first part of our experiment is the volume control circuit. Here's a circuit diagram of the volume control circuit. Running from the voltage runs from Vin across one resistor into a potentiometer, where one end goes to ground, the other one runs across another potentiometer, and then it goes to Vout, which is measured relative to ground. The potentiometer has alpha values of 0 to 1, with 1 being set to the full resistance, in this case 108 kiloohms, and 0 being set to no resistance, and it varies linearly across that relationship.
So we have, this is like a little theory of how we managed to get V out over V in as an equation. Basically, start off, V out over V in is going to equal, when you take the V out here, it basically acts like a voltage divider that takes the equivalent resistance of these two pieces over the resistance total across the entire circuit. So basically, when R2, the potentiometer, is divided up, you have R2A, R2B top and bottom, and then R2A is when alpha equals 1, R2A is full, alpha equals 0. When alpha equals 0, R2A is full. When alpha equals 1, R2A is 0. When R2B, when alpha equals 0, R2B is nothing, and then when alpha equals 1, R2B takes all of the resistance of R2. So basically that's how we decided to write R2A and B as a function of alpha. And then next we needed to write R equivalent as a function of R3 and R2B, and then R total as a function of R1, R2A, and R equivalent. And then basically bring these two things into V out over V in is how we write the transfer function of our volume control circuit as a function of alpha. So basically from here, you get these here and over.
We tested out our, as you can see, we tested out our volume control. And this plots the V out over V in ratio versus alpha, which has a clearly exponential relationship. Our experimental and theoretical data matched up very well, as you will see as a trend in our experiments.
Hi, so for the second part of our circuit, we'll have to design an audio preamp that selectively amplifies the treble and the bass frequencies independent of each other. So you can see here, this is the basic circuit configuration we were provided, and from the instructions we were able to selectively discern the specific components that contribute to treble and to bass. So according to the frequencies that according to the selective combinations of boost and cut that we needed as a result of design criteria requirements, we selectively diagrammed our circuit, both treble and bass independent of each other, and in the following configurations: full boost, cut, and flat for treble, and then full boost, cut, and flat for bass. So basically, what we're expecting is that for the highest frequencies, we would be able to get a gain of 10 times, which is a decibel gain of 20 times for a full boost scenario, and a cut of 1/10, which is a decibel loss of -20 for a full cut scenario, and no boost or gain for a flat scenario, and similarly for the bass as well for the low frequencies. So basically, the next step we had to do was how we were able to pick the selective capacitor and resistor values, so that we can satisfy the requirements of 10 boost and 10 gain. So basically, we we started off, we needed to figure out, as a result of an inverting amp, what is the ratio of gains. And as we know from studying inverting amplifiers, that is the impedance that connects the output and the inverting input to the impedance that connects the input and the inverting input of the op amp. So basically, we diagrammed the selective components that contributed to these respective impedances. So as you can see from these values, we should have picked that C's, if we had the same capacitances, regardless of frequency at flat, the V out over V in the V out over V in was going to equal 1, and there was going to be no effect from the tonal control. And similarly, from full boost and full cut, we needed to pick values that gave us 10 or 1/10. So basically, if you look at these, at high frequencies, basically these circuits are shorted out, and we only have R5 and R4s contributing to the circuit. So basically, R4 needed to be, or the maximum value of the potentiometer needed to be around 9 to 10 times larger than the resistor. And similarly, same logic over here for base for accomplishing the 10, 1/10, and 1 is that for low frequencies, this value J omega C is practically 0. So basically, again, we run into the scenario of a ratio of resistors. And similarly, if we pick the same capacitors and the same R1 and R3, then this will remain 1. And then for the same values here, we would need our potentiometer to be around 9 to 10 times larger than the value of each one of these resistors, so that we could achieve the ratio of impedances that will give us the 10 times and the 1/10 gain. So and there is where we made our initial judgment of values.
Overly manly, man.
Here's our circuit diagram for our active audio preamp circuit. As you can see, the values are displayed on the diagram. Our actual circuit is built as such. The V in from the source of the iPod goes in, where it is split between the treble filter and the bass filter. The bass filter has 2 capacitors and 2 resistors centered at a potentiometer, the wiper of which is sent to the inverting input of the amp. The treble potentiometer has 2 capacitors and an R5 value running from the wiper to the inverting input. From the non-inverting input, another resistor leads to ground. From the output of this preamp, the Vout runs to the volume control circuit, which we have previously explained, and then it runs to the speaker. In building this circuit, we used some trial and error and some game time adjustments to change the values of these capacitors, as well as R5. We ended up decreasing R5 and tried many different values for these capacitors of C3 and C4. First trying larger ones, then smaller, and settling on a value of 27 nanofarads. Okay.
Go.
The reason for changing these values of the capacitors in R5 was that initially we had issues with current from low frequencies flowing into the treble part of the circuit and currents from high frequencies flowing into the bass. The presence of these currents acting interfered with the amplification, especially for the treble part, where we had a good deal of difficulty getting sufficient amplification and sufficient degree of the cut. We didn't have as much problem with the bass. But once we were able to find values that worked, we were able to settle on it and get the amplification that you will see in the bud plots.
Action.
Hello. This is proof that the previously demonstrated circuit design actually functions as built. As you can see, for the treble boosted and the bass cut, it has a high gain of about 20, just under 20 decibels for high frequencies, and strongly cuts off the lower frequencies. For the bass boost and the treble cut, the opposite is true, with low frequencies having a high gain, and that declining down to a large cut for low frequencies. High frequencies, sorry. And then for the flat, when both of the knobs are turned to flat, we basically have a relationship of 0, no gain. For each case, for the bass boost and the treble cut, as I previously described, at low frequencies there's a high gain, and at high frequencies it strongly cuts them out. As you can see, the blue diamonds are experimental data and the red diamonds are theoretical data. These two match very, very closely for this, proving that our theory and our design matched up very well. This is the plot for the bass cut and the treble boost. For low frequencies, it cut it off, and for high frequencies, it gave us a very strong gain. This is basically the inverse of the previously shown chart, which is what we would expect as the knobs are turned to opposite positions. Again, our theoretical and experimental data matched up very, very well. The last one is when both the bass knob and the treble knob were turned all the way flat. These theoretically should have a gain of 0, as both of them are set to neutral positions. As you can see, again, our data matched up very, very well. It's a flat line along gain of 0.
Okay, now we're actually going to see our circuit working in real time with an iPod in the circuit. So
Do you like the little clip I put of Johnny?
All right, so now the song is playing. We're going to start with our volume control.
Wait, which one is this? It was last.
You can see that sound is now coming through. And you can see that input and the output waves are moving. Now we're first going to amplify the treble frequencies with the bass frequencies all the way down. As you can see, as you can hear, the voices and the higher frequencies of the song are now much more obvious. And if you look under the scope, you see the treble frequencies flashing hard, like the close frequencies are spiking high right now. So now we're going to turn the treble frequency down, and treble frequency is much less apparent on the screen as well. So now we're going to turn up the bass frequencies, and bass knob turning. You can probably hear it right now in the background. The subwoofer is booming pretty loudly there, and on the scope you can see the long wavelength waves spiking at the moment. And now we're going to turn them both up together. So the bass is up, and we're going to run the treble as well. So, real quick, this sums up the last part of our project, which is the opto communication link, which is supposed to send our sound wave via a laser to a speaker. So basically, this is how we propose that this would work. We start off with a battery grounded at its negative terminal with this positive terminal running to an iPod. And then taking that iPod, we run into a lead resistor and into a red LED light, which is grounded. So on this side of the circuit, which is a transmitter, you have the battery, which is a constant DC source, and the iPod, which is a varying sound wave, combining to serve as sort of like a varying AC power source. The battery providing the power, and the iPod providing the wave, and it passes through a lead resistor and then actuates the LED. Now, for a red LED, it takes 1.5 to 2 volts of voltage to actually actuate it. So basically, this is sort of, and then after it's actuated, the voltage across the LED stays constant, and then the current increases, and it varies the brightness of the LED. So therefore, this is the equation that will govern the brightness of the LED, the current of across the LED, which will in turn govern its brightness. And then it's going to be the input wave, the AC input wave, minus the wave across the diode, and then divided by the lead resistor. And so we decided to pick a lead resistor of a kiloohm. So for a standard like 9-volt battery, it'll give us a range of like 0 to about 6 or 7 milliamps, varying across this diode and varying across this LED, which is good because well, the LED would not allow any current to go negative on here. And then once this varying light is picked up over here by a photoresistor, and then the component values of photoresistor and a constant resistor which is grounded with a 9-volt battery. Basically, the resistance of this resistor varies with the intensity of this light, which varies with the current across the diode, and then that which varies according to the voltage across the iPod. Therefore, and then from here we lead a V out to the speaker, which serves as and that V out is sort of governed by this current divider, which takes the resistance of the photosensitive resistor over the total resistance across this whole circuit. So as this varies, the V out over V in varies according to the original sine wave coming from the iPod and the battery.